Hello, this video will go over the final exam review sheet solutions. All right, number one, two instruments are used to measure the height h of a tower. The error made by the less accurate instrument is normally distributed with a mean of 0, standard deviation 0.0056 times h. And the error made by the more accurate instrument is normally distributed with a mean of 0, standard deviation 0.0044 times h, and the errors from the two instruments are independent of each other. Calculate the probability that the average value of the two measurements is within 0.005 h of the height of the tower. So we're finding a probability about the average of two random variables. So we're going to find the mean and variance for the average of the two random variables. So we want the expected value of the average, which is x1 plus x2 over 2. We can factor out the 1/2 and apply the expected value individually to each. Since each expected value is 0, 0 plus 0 times 1/2 is 0. So the expected value of the average is still 0. Now, we need standard deviation, but we're going to work with the variance because the variance is additive when the variables are independent. So we can calculate the variance of x1 plus x2 over 2. We factor out the 1/2, has to be squared, becomes a quarter, times the sum of the variances. Now we're given the standard deviation, so the variance we have to square. So we have to square each of those values, 0.0056 squared h squared plus 0.0044 squared h squared. All that times a quarter is the variance of the average. So factoring out an h squared and adding up these squares of decimals, we get h squared over 4 times 0.00005072. That's the variance of the average, but we need the standard deviation, so we can take the square root of that, and it comes back down to 0.00356h. And we want the average value to be within 0.005h. Now, each of these is normally distributed, so the mean will be normally distributed. Let's call that y. We want the y expression to be within 0.005h, so plus or minus 0.005h. We're going to convert this over to a z-score so we can look it up on the chart. So we're going to do the random variable minus the mean over standard deviation. The mean was 0, standard deviation 0.00356h. So 0.005h minus 0 divided by 0.00356h is 1.40. And on the negative side, we get the same thing, negative 1.40. And then you have to look this up on your z-score chart. We have the probability that z is between 1.4 and negative 1.4. Using the chart, it's 0.9192 minus 0.0808, which is 0.8384. All right, small comment here on the standard deviation. So again, we have to work with variance. So we have to do the square root after the fact. So we do a squared plus b squared, then take the square root to get the standard deviation value. This is just a little comparison to see which one is bigger, adding directly, which would be wrong, or doing square root some of the squares. And it does turn out that the right-hand side is a little bit bigger. Again, just an aside there, not really necessary to answer this problem, but just an interesting fact about the calculation of the standard deviation when you're dealing with a sum. Okay, number two. Suppose x is a normally distributed random variable with mean of 100 and variance 100. What's the probability that x is between 80 and 120? So we have a normal distribution. We're going to convert it over to the z-score so that we can use the chart. Z-score formula, x minus mean over standard deviation. So if to take the root there, so it's 80 minus 100 divided by the root of the variance, which is 10. And so that's negative 20 over 10, which is negative 2. And when we do the other side there, 120 minus the mean of 100 divided by the root of the variance, we get 20 over 10, which is 2. So it's the probability that z is between negative 2 and 2. Looking this up on your chart, the value for 2 on the table is 0.9722, and a negative 2, the table value is 0.0278. You subtract those and you get 0.9544. So it's about a 95% chance. Now, part B is the same question, but we don't know whether or not we have a random variable that's normally distributed. It's unknown. So what can we say about a random variable with unknown distribution, but we know that the mean is 100 and variance is 100? What's the probability that the variable is between 80 and 120? So we cannot use a normal distribution. We have to use Chebyshev's law for an unknown distribution. The probability that absolute x minus mu greater than or equal to k times sigma is less than or equal to 1 over k squared. So the probability of being more than k standard deviations away from the mean is less than or equal to 1 over k squared. So we just have to count out here how many standard deviations are we from the mean. The standard deviation here is the root of the variance. It's 10. 100, the gap from 100 to 80 and to 120 is 20. It's 2 standard deviations. So the probability of being at least 2 standard deviations away from the mean by Chebyshev, it's less than or equal to 1 over k squared, 1 over 2 squared, which is a quarter or 25%. So there's a 25% chance that y will be beyond 120 or 80. So we do the opposite probability for in between 100 minus 25. It's going to be at least 75%. So there's at most 25% outside that range, at least 75% inside that interval 80 to 120. All right, number 3, calculate the moment generating function, MGF, for an exponential random variable with density 2e to the negative 2x for x greater than 0. So the moment generating function, we're doing expected value e to the tx. So we're integrating over the domain e to the tx times the density. So it's e to the 2x times 2 e to the minus 2x. Factor out the constant 2. Combine exponents there, we get e to the power tx minus 2x. Factor out the x, we get e to the t minus 2 times x. The integral of that is just itself divided by the coefficient of x divided by t minus 2. And we're taking the limit here. Improper integral, b goes to infinity. So we get upper minus lower here. We plug in the b, plug in the 0. All right, so b goes to infinity here. As long as t is less than 2, this will be a negative infinity, and then the whole expression will go to 0. So this portion will go to 0. And the second part, e to the 0, is 1. So this is 2 over t minus 2. So this will converge for t less than 2. We get e to the minus infinity, so this goes to 0. So the limit is 0 minus the second expression, so it's minus 2 over t minus 2. So moment generating function, negative 2 over t minus 2 for t less than 2. All right, number 4. Suppose that earthquakes occur in a region according to a Poisson distribution at a rate of 2 per week. Find the probability of at least 3 earthquakes in the next 2 weeks. So we have to adjust for the change in the time length here. We have 2 each week. We want to study 2 weeks. So that's going to be 4, 2 per week. So that's 4 every 2 weeks. I'm actually doing part B here first. So 2 per week means 4 every 2 weeks. So the mean is 4. We want at least 3 earthquakes. At least 3 means 3, 4, 5, 6, and so on. So we count the opposite, 0, 1, and 2, and subtract. So we're going to calculate the Poisson distribution here for, remember, mean is 4. And we're going to go through the values less than or equal to 2. So 0, 1, and 2, and then subtract 1 minus all that. So it's e to the minus lambda, lambda to the x over x factorial, e to the minus 4 times 4 to the 0 over 0 factorial minus, well, after distributing, it becomes a minus e to the minus 4 times 4 to the first over 1 factorial minus e to the minus 4 times 4 squared over 2 factorial. And then you could plug this into a calculator. You don't have to leave it in exact form. You can just put it into decimal form here. And then the first part was, I think I have these labeled backwards here. So the other part was the moment generating function, expected value of e to the tx. We have a discrete situation, so we're summing e to the tx times the PMF, which is e to the minus lambda, lambda to the x over x factorial. We're using the original format of the rate there, 2 per week. We can factor out e to the minus 2 in the front. We have 2 to the x and e to the t x. So we have 2 e to the t to the x power over x factorial. And then this series here is the power series for e. It's e to this argument, 2 e to the t. So e to the minus 2 on the outside, e to the 2 e to the t from the series. Multiplying together, we add exponents. It's 2 e to the t minus 2. All right, number 5. Scores on a certain exam were normally distributed with a mean of 81 and a standard deviation of 4. Find the probability of getting an exam score less than 79. Find the minimum exam score needed to be in the top 10%. So we want the probability x is less than 79, mu is 81, sigma is 4. We convert this over to a z-score so we can look it up on the chart. We're going to convert the 79 from an x to a z-score. 79 minus 81 over 4. It's negative 2/4. It's negative 0.50. So we want the probability that z is less than negative 0.50, and that is 0.3085. Second part, find the minimum exam score needed to be in the top 10%. So to be in the top 10% means there's 90% to the left or 0.90 to the left. So you have to look in the body of the table for 0.9000 and then read off the closest z-score. It's in the 1.2 row, 08 column, so 128. And then we convert this back to an x value, z times sigma plus mu. So 128 times 4 plus 81. 128 times 4 is 5.12, plus 81 is 86.12.